So the first thing I'm going to do is I'm going to look at my question. I'm going to work out what are some important details and bits of information that they've said up the top here first. Okay, so I've got a mass of 65 kgs and another mass of 50, so those two are quite important. I've got a direction to the right, and I've got this constant velocity of 66 meters per second here. I've then got another direction, again to the right, also at a constant velocity of, this time, 8.5 meters per second. And then we get this scenario of Katie collides with Aroha, holds her shoulders, and they move together. Now that's important, to the right at a constant velocity. So there's quite a lot of information here already. Okay, they've also helpfully got a diagram for us this time. So if we look at this question, we've got some masses, we've got some velocities. This question looks to me like it's about momentum. Okay, so what physical quantity is conserved? Now conserved gives you that clue. Okay, we usually have two things that are conserved, either energy or momentum. Okay, so what physical quantity is conserved in the collision that they've described here? Okay, so that's going to be momentum. Momentum is conserved. Now, this is important as well. State any assumptions you have made. Okay, so we have to assume that there are no external forces in this situation, like friction, for example. So, assuming no external forces. Now this to me looks like it's probably an achieved question. Okay, so we've got a state kind of situation. All right, then what we need is we've got calculate the combined velocity after the collision. So we've got this final velocity that we're trying to work out. Okay, well, how do we work that out? Because we've been looking at momentum, this is also going to be a momentum question, okay? And our initial momentum, Pi, because momentum is conserved, it is going to equal that final momentum. Okay, so what do we have? Let's start with what we've been given. We've got a mass of Katie, which is 65 kilograms. We've got a mass of Aroha, which is 50.0 kilograms. We've got a velocity of Katie, which is up here at 8.5 meters per second. We've got a velocity of Aroha at 6 meters per second. Okay, so we can work out our initial momentum from this. That's quite useful. Okay, so momentum is mass times velocity. Okay, and if we have more than two things, so we have Katie as an individual and Aroha, we've got mass of Katie times the velocity of Katie plus the mass of Aroha times the velocity of Aroha. So all we need to do is just substitute those numbers into here. So 65 times 8.5 plus 50 times 6 so we will have a momentum of 552.5 for Katie and 300 for Aroha. So our total initial momentum, we just add those two together, is 852.5 kg meters per second. So that is our Pi. All right. Now, we've set up here that momentum is conserved. So our initial momentum is going to equal our final momentum. So PF is also going to equal 852.5 kg meters per second. All right. Now, we're trying to find their velocity. So we're trying to find v. So we need to rearrange for v. So our velocity is going to equal our momentum divided by our mass. Now remember, this is our combined mass of Katie and Aroha. So we're going to have 852.5 divided by our mass of Katie plus our mass of Aroha. So we need to do our 852.5, that's our momentum, divided by 65 plus 50, and we will get a final velocity of 7.4 meters per second. And they've stated up here to the right. Okay, so that there is our final answer for that question. Okay, so this is the equation you get given. This is us rearranging to find force. Okay, momentum over time is our force. Okay, that's just rearranging this. So it's not just any momentum, it's our change in momentum. Okay, so what we need is we need to work out the momentum that they have in the final one minus the momentum that Aroha has initially. Okay, so we've got our change in momentum equals final minus initial. Okay, so that's going to be our final momentum. Remember, we can reuse the momentum that we had from our previous question. Okay, or our velocity from our previous question rather. So mass times velocity minus mass times velocity. So our mass is going to stay the same. Aroha is 50 kilograms. Our final velocity was that 7.4 that we worked out in the previous question. Okay, so we're going to do that together, and then we're going to minus our mass again, which is staying at 50 because Aroha hasn't changed. And then we're going to times that by her initial velocity, which was 6. That was in the top bit of that question. Okay. So what we get is we get 370 for Aroha's final momentum minus 300 as her initial. So our change in momentum, our impulse, is going to be 70. Okay, so that's the first pass. We haven't actually answered the question yet. Okay, so we've got this change in momentum. We can now use this equation, our impulse equation, to work out the force. Okay, we've been given a time, we've got a momentum, we've got our change in momentum, and we need to work out a force. Okay. So let's start off with our equation that we've been given. Okay, we then need to rearrange it to be for force. So we're going to do change in momentum divided by change in time. So then we're going to do 70 divided by our time of 2.5 seconds. Okay, so 70 divided by 2.5, and that'll give us a force of 28 newtons. Okay, now that's our second merit question. So getting all the way to this final force gets us a merit. Getting to this point gets us an achieved. Okay, so just identifying that you need to do impulse and you need to calculate this change in momentum can get you to an achieved. All right, let's have a look at this last question. So they're still on roller skates, but we've moved away a bit from this momentum idea. So let's have a look at what we've got. So Katie's going down a carpeted ramp at some constant velocity that we don't know. On the diagram below, the friction force, which is down here, is shown. Draw and name, so there's 2 instructions there, all other forces acting. Okay, now the easiest one to do is one that always goes down. Okay, so we draw it from the bottom of Katie just directly down. Okay, and that is our weight force, okay, or Fg, the force of gravity. Okay, so that's one going down. We're going to have one going up. Okay, now this one is at an angle, so it's going to be at right angles with our surface. There's a little right angle in here. Okay, that's going to be at right angles with our surface, sort of going straight up through Katie. Okay, and that is our support force or the reaction force. Okay, so you can put an R or you can put an S. That's our support force. Okay, so getting to there, that gets us sort of an achieve level. Can we draw some arrows and identify what they're showing? All right. The next question, in the box below, draw a closed vector diagram showing that the forces acting on Katie are balanced, and name each force. Okay, so a closed vector diagram is one of those vector triangles. Okay, so there are sort of 2 possible ways we can flip this. I'll draw both. Okay, so option A is we can start with our reaction force as sort of our base. Okay, so our reaction force is going off at some angle. Okay, then we've got our force of gravity going straight down, so Fg. All right, and then we close this, and this force is our friction force. Okay, so that's one of our closed vector diagrams. You can also draw it by starting with the force of gravity as your base. So force of gravity is your base. Okay, remember that they're all going head to tail, so that is our reaction force. We've basically just shifted it down, or our support force. And then here again, we're going to have our friction force. So getting both of these, getting all of that correct, okay, gets you to excellence.